The continuous growth in electricity demand, combined with an aging power infrastructure and a shift towards sustainable energy sources, has placed unprecedented strain on the electrical grid system. As we integrate more intermittent, renewable energy sources like solar and wind into our energy mix, the complexity of managing this system only continues to grow. Traditional grids were not designed to handle these new challenges, leading to issues like increased energy waste, higher operational costs, and reduced reliability. But there is a solution, one that lies in the fusion of cutting-edge technology and forward-thinking strategy: smart metering and data analytics. Renewable energy like solar and wind are inherently variable and intermittent, meaning their output fluctuates based on factors such as weather conditions, time of day, and seasonality. This unpredictability makes it challenging to forecast energy supply and demand, leading to potential imbalances that can affect the grid stability and reliability. Smart meters are sophisticated devices that have replaced traditional mechanical or analog electricity meters. Unlike traditional meters, which require manual reading, smart meters can transmit energy consumption data automatically and continuously. Smart meters equipped with voltage sensing capabilities can monitor voltage levels in real time, providing utilities with valuable insights into the quality and stability of the electricity supply. By enabling remote disconnection of faulty elements, utilities can significantly reduce energy losses due to faults or equipment failures. Smart meters provide utilities with advanced metering infrastructure, ME, which enhances the accuracy and reliability of energy consumption data. This improved data quality enables better grid planning, operation, and maintenance, leading to increased grid stability and reliability. Data analytics involves the systematic examination and interpretation of vast amounts of data to extract meaningful insights and support decision-making. In the context of the power grid, data analytics plays a crucial role in various aspects, including predictive modeling, anomaly detection, and fault identification. Grid operators can leverage data analytics algorithms to continuously monitor real-time grid data, identifying any unusual or abnormal patterns. These anomalies could indicate issues such as equipment failures, cyber attacks, or unauthorized access. By analyzing data on equipment performance, energy flows, and grid operations, data analytics tools can identify areas for improvement, suggest optimized operational strategies, and highlight potential bottlenecks. Building a strong data-driven culture that encourages data-informed decision-making across all levels of the organization is also crucial. This data-driven approach allows grid operators to enhance the overall efficiency of the power grid, reduce operational costs, and improve the reliability of electricity supply. As we continue to grapple with the challenges of meeting growing energy demands while transitioning to cleaner energy sources, the power industry must embrace these innovative solutions. By investing in smart metering infrastructure and harnessing the power of data analytics, we can pave the way for a smarter, more sustainable energy future. Embracing data analytics is essential for utilities and grid operators to enhance the reliability, efficiency, and resilience of the power grid in the face of growing challenges. If you enjoyed this video, you might also like another video we did on the digital transformation of the electric power industry. You can find the link in the description below. By detecting anomalies promptly, grid operators can take swift action to mitigate risks, prevent widespread outages, and safeguard the integrity of the power system. Moreover, ME enhances outage detection and isolation capabilities, allowing utilities to identify and isolate faults quickly, minimizing the impact and duration of power outages. Analyzing data from various sources, such as smart meters, sensors, and historical records, allows for the quick identification and diagnosis of faults or equipment failures. This capability enables grid operators to respond rapidly to outages, minimizing the impact on customers and ensuring the power grid's reliability. This is particularly crucial in the face of increasing extreme weather events and cyber threats. Additionally, smart meters facilitate demand-side management, allowing utilities to communicate with consumers during peak demand periods. While the initial investment costs for smart meter deployment can be significant, the long-term payoffs in terms of increased efficiency, reduced losses, and enhanced grid reliability justify the investment. This enables consumers to reduce their energy consumption voluntarily or even shift their usage to off-peak hours, helping utilities avoid costly emergency measures. Furthermore, smart meters support the integration of distributed energy resources like solar panels and battery storage systems. By analyzing historical data on energy consumption, weather patterns, and grid infrastructure, data analytics tools can develop predictive models that forecast future electricity demand. These forecasts allow grid operators to anticipate fluctuations in supply and demand, make informed decisions about resource allocation, and plan for future expansion needs. This proactive approach helps ensure that the grid has sufficient capacity to meet future demands while minimizing costs and improving efficiency. These systems can sell excess energy back to the grid through smart meters, contributing to a more diversified and resilient energy supply. Moreover, smart metering facilitates the implementation of time-of-use tariffs, which incentivize consumers to shift their energy usage to off-peak periods when electricity prices are lower. This flexibility allows utilities to optimize the use of available generation capacity and reduces the need for costly infrastructure expansions. By detecting voltage fluctuations or other power quality issues, utilities can take proactive measures to mitigate these problems, ensuring a more reliable electricity supply. This capability is particularly crucial in areas with high penetration of renewable energy sources like solar, which can cause voltage dips when the sun is not shining. This eliminates the need for physical meter readers and reduces the risk of human error associated with manual data collection. Automated meter reading also provides up-to-date information on energy usage, allowing utilities to generate accurate bills and detect anomalies or potential issues promptly. Furthermore, smart meters enable remote control capabilities, allowing utilities to remotely connect or disconnect customers in case of non-payment or to manage peak demand. This capability helps utilities balance supply and demand more effectively, reducing the need for costly infrastructure upgrades. They offer numerous advantages over their predecessors, including real-time energy monitoring, automated meter reading, and remote control capabilities. With real-time energy monitoring, both consumers and utility providers can track energy usage instantaneously. This immediate feedback allows consumers to make informed decisions about their energy consumption patterns, leading to more efficient energy usage. By understanding when and how much energy is being consumed, households and businesses can implement energy-saving measures and shift their energy usage to off-peak hours when electricity prices are typically lower. Furthermore, as more distributed energy resources, DERs such as rooftop solar panels and battery storage systems become prevalent, the traditional centralized power generation and distribution model is evolving. This shift poses new challenges for grid operators who must now manage a more dispersed and complex network with multiple smaller energy producers and consumers. In this video, we lines delve into how these innovative solutions can help us overcome the challenges facing our energy grids today. Smart metering refers to the deployment of digital network devices known as smart meters that provide two-way communication between energy suppliers and consumers. These meters enable real-time data exchange, allowing for dynamic pricing, demand response, and remote monitoring of energy usage. Data analytics, on the other hand, involves the application of advanced statistical and computational techniques to extract meaningful insights from vast amounts of data. When applied to the power grid, data analytics can optimize grid performance, enhance efficiency, and improve the overall reliability of the energy system, and pave the way for a more sustainable and efficient energy future. Let's begin by examining the power grid itself and the challenges it faces. The power grid is a complex network of interconnected systems that transmit and distribute electricity across large geographical areas. Historically, the demand for electricity has grown steadily due to factors such as population growth, industrialization, and increased usage of electrical appliances. However, the pace of this growth is accelerating, driven by rising living standards, urbanization, and the adoption of energy-intensive technologies. At the same time, a significant portion of the existing grid infrastructure is aging and nearing the end of its service life. Many electrical components, such as transformers, circuit breakers, and transmission lines, were initially designed with an operational lifespan of 25 to 30 years. Now, several decades later, they continue to operate beyond their intended lifespan, raising concerns about their reliability and capacity to handle the growing demand. The situation is further complicated by the increasing frequency and severity of extreme weather events. These events often result in widespread power outages, damaging equipment, and interrupting the supply of electricity. As we work towards a cleaner energy future, the integration of renewable energy sources adds another layer of complexity to the grid's operations. To address these pressing challenges, the power industry is turning to advanced technologies and data-driven solutions, namely smart metering and data analytics. Let's first look at how smart metering is revolutionizing the way we use energy. Automated meter reading is another significant benefit of smart metering. Now let's explore how smart metering enhances grid performance and reliability. One key aspect is voltage and power quality management. Another important contribution of smart metering to grid performance is loss reduction. However, the benefits of smart metering extend beyond grid performance and consumer behavior. It also plays a vital role in enhancing overall grid security and resilience. As we have seen, smart metering brings substantial benefits to both consumers and utility providers. Now, let's turn our attention to the role of data analytics in optimizing grid performance. Predictive modeling is essential for anticipating future trends and optimizing grid operations. Anomaly detection is another critical application of data analytics in the power grid. Fault identification and diagnosis are also greatly enhanced by data analytics. Furthermore, data analytics contributes to improved operational efficiency in the power grid. To harness the power of data analytics in optimizing grid performance, utilities and grid operators need to invest in robust data management systems, advanced analytics software, and skilled data analytics personnel. As we have seen, data analytics offers numerous benefits for the power grid, from predictive modeling to anomaly detection, fault identification, and improved operational efficiency. The integration of smart metering and data analytics holds immense promise for transforming the power grid into a more efficient, reliable, and sustainable energy infrastructure. Thank you for watching. If you found this video informative, please remember to subscribe to our channel for more insightful content on data analytics and other technical topics.
So now, a bit about me. My name is Mike L., and I am an experienced electrical engineer who has worn many hats, holding key roles in projects, engineering, planning, operations, asset management, maintenance, and field resources development. I design and pioneer engineering solutions to propel the utility and energy industry forward. My passion within the industry has also driven me to develop educational materials for the new generation of utility and energy professionals. The knowledge I teach is not only based on my own experience within the power utility industry, but also on knowledge gaps identified by other professionals in the field. Learning from me will provide you with the comprehensive, fundamental knowledge you need to kickstart your professional career in the utility industry. If you are interested in what I have to teach, check out my courses at Udemy and connect with me on LinkedIn, X, and Facebook. Don't forget to comment, like, and subscribe this video. Bye for now.